Well, let's bring David Scott in at this point because, David, you are professionally a structural engineer. So let's run through some of the information that we know so far.
Can I just before we start on the technical, we just say a wee word about the fire service. The clip from Boris Johnson was very interesting, as much for what he didn't say, because there has been a huge reduction in fire incidents in the UK. Since 1999 to the present day, it's roughly halved. So it's not necessarily unreasonable that if you have half the number of call-outs from the fire service, you might need fewer stations and or people. But of course, what matters here is response time and the ability to deal with incidents when they do come up. So it was a very ignorant response from Boris Johnson there. And we're seeing similar ignorant attempts to use this for political capital from the Labour Party just now, because remember, the fire service were there in 6 minutes. So it doesn't seem to have been a response time issue. And they seem to be pretty well resourced. The problem here is somewhere else. But I would simply point out that in looking at the fire service, the driving impetus must be to get the right people at the right time where they're needed, not necessarily any given set staff or establishment.
Well, yeah, that's right, David. But of course, if you close fire stations, you don't have the personnel, as you say, close by. If you have an incident of a certain scale, which this was, and okay, this incident was unprecedented because we haven't seen this type of fire in this country before. Then, if you don't have the personnel available because of cuts or for whatever reason, then you can't deal with incidents of this scale when they happen. So are the deaths then just an acceptable level of risk? Is that what we're talking about?
Well, obviously that shouldn't be what we're talking about. But what my point is that if you're having half the number of incidents, and the reason for this, incidentally, is nothing to do really with the fire service or indeed with the population, other than we're smoking less. Habits have changed, and oven chips have made a huge difference because people don't have chip pan fires anymore because they have oven chips, and furniture is less flammable. So these things have made a huge impact in the number of fires we're having, which is excellent. So the fires have halved. So there must be some response to that, but the response must be an intelligent one that maintains the ability to deal with major incidents, not one that's driven simply by money saving or by some sort of crude approach where half the number of fires equals half the number of firefighters, which would be nonsensical.
David, just to reinforce you on that, we had the situation here in Plymouth and the surrounding area that the limitation at one stage for the fire service was that they didn't have a high-rise ladder available. So obviously this is one of the vehicles with an extremely high capability for the ladder. And the government solution was that, well, okay, you can share that facility in the region, which meant, of course, if there was a serious fire in a high-rise building, even if you could get the fire tenders there, they couldn't fully act on the fire because they didn't have this extended ladder capability. Now, I'm not sure how that got resolved, but I know that a few years ago, this was a very, very hot discussion point between the local fire service, who were trying to do their job, and a government that was making what can only be described as stupid and ridiculous cuts.
Let's move on to this then. So, David, take us through this. The work happened a year ago, was it?
Yes. So Grenfell Tower, designed 1968, built 1974. It was complete. It's a concrete building. It's not clear to me whether it was built in situ concrete or precast large panel systems, which affects the robustness of the structure. But built in at the peak of the high-rise building boom, early 70s, and designed before but built after Ronan Point, the famous progressive collapse of a large panel system building.
And this is the company that did the work, is that right? Yes, it is, yeah.
Yes, so the work was completed in summer last year, an 7.8 million pound refurbishment, which was inside and out. So we had new services, You see here the very plush gym, very nice looking building, and it was overclad to improve its appearance, its durability on its external surface,
so we have
its
the sun
insulation.
Here, showing before and after pictures to show how the refurbishment looked.
So the outer cladding you see here is a flat panel in aluminium, a very attractive architectural product that transformed the building's appearance from somewhat sad and unloved 1970s tower block to something much more 21st century in appearance. And this material is one we're going to concentrate on today. So the overcladding system is as follows. There's an insulation board applied directly to the original outside surface of the building. This is PIR, polyisocyanurate foam, and a bit more on that later. So that was 100 millimeters of that foam. There was then a 50 millimeter cavity, and then there's this outer cladding which is only 6 millimeters thick, and it's a composite board, and it comprises two layers, an inner and outer layer of very thin aluminium, 0.5 millimeter aluminium, and a core of low density polyethylene, so polythene core, and that's the area that we should be concentrating on in terms of what went wrong here, what went so tragically wrong. The Herald here has a description of the material, and it's identified the product correctly, as I understand it. And so what I want to talk about is how we've got to this situation and what these materials are actually like. There are regulations and there's good industry guidance governing how tall buildings are overclad. The risk of fire spreading up the outer cladding has been well recognised for some time. There have been worldwide several very major incidents. So what you see on screen here is the guidance document for Celotex RS5000. This is a PIR insulation that was applied to the outside of the building. And the little diagram you see there is taken from the industry standard guidance document on this subject. And it illustrates exactly the problem that happened here. It illustrates that either you have an outer cladding that is resistant to fire and only burns very slowly. So as a fire in a flat reaches what's termed flashover. Now that's a point where the atmosphere inside the compartment where the fire is gets so hot that everything combusts. So the temperature rises and rises and rises, gets to a point where everything in the room catches fire. And then the temperature then peaks. It's called flashover. So you get a very rapid temperature rise. This destroys things like windows, and the fire breaks out to the outside. Now, one of two things happen, and they're illustrated in this diagram. Either that then slowly works its way up the building, gets in through a window on the floor above, sets light to the contents in the flat above, which they then have to slowly burn, reach this flashover point, and then the process is repeated. So the fire progresses very slowly up the building. On the other hand, if the fire can spread up the cladding, then all floors right to the top of the building are immediately affected by secondary fire, and the whole building's engulfed very rapidly, which is exactly what happened here.
And the point here, David, is that so the point that you're making here is that this is a well-recognized problem.
The risk was known, was correctly identified. People knew exactly what we were trying to avoid. Right? This was not a surprise that this could happen. Now, the material PIR was tested. Now, a little bit about the test. This next slide illustrates the nature of the wall construction that was tested, which is different from the nature of the wall construction that was built. Now, what the test involves is a section of wall being built with an aperture in it representing a window, and a basket with a great deal of timber is placed in that, and the thing's set alight. And I think it's allowed to burn for half an hour, and then the burning timber is removed. So this represents a fire breaking out through a window and setting light to the cladding, affecting the cladding roundabout. So the window is modelled in this test. It's half an hour of a very intense fire, and then the combustion source is removed, and the test is continued for another half hour to see how the cladding, how the fire progresses in the cladding. And a successful test is that the fire does not get to the top of the test panel, which is 6 meters high, in 1 hour. So that's the standard. The fire should spread no more than 6 meters in 1 hour. Now, in minutes, this fire spread to the very top of the building. So something very different from the test performance has actually happened here.
When I looked at the documents that you sent me, David, there was a statement in it which suggested that this type of cladding shouldn't be used on buildings over a certain height. Is that correct?
Well, this relates to the PIR insulation foam. Most PIR insulation foam isn't suitable for buildings over 18 meters, and this is due to its fire performance. This particular PIR foam was allowed to be used in much taller buildings because it had satisfied this test. Now, the test was run with the foam insulation that was used on the building and a different outer cladding, a glass reinforced plastic, which is a solid board and much more durable. So the cladding had been changed on the outer for architectural reasons. The cladding had been changed, but the test was still considered valid. And the reason that the test was still considered valid was that the classification of the outer cladding was the same as Class O, which is a measure of how flame spreads across the surface. So that's one thing I'd like to come back to, is just what these tests actually measure, because they measure certain specific things. So we had a successful test on the PIR foam with a cladding material that showed that the flame wouldn't propagate rapidly on the building. And on the basis of that test, this system was authorised. The actual outer cladding was changed from one material to another, and but they had the same official rating in terms of surface spread of flame. So nobody thought, the regulators, the designers, the contractor, thought they were operating within known areas that were covered by testing, but they weren't, for a reason which I'll try and pin down now. This surface spread of flame test it tests the paint on the cladding, essentially. It only tests the surface. It's there to make sure that fire can't propagate rapidly across the surface and cause rapid spread from one area to another. But it's a small flame source. It's held on the material for 1 minute. So it's very small amounts of heat, 1 minute. And then it's removed and the test is observed for another 10 minutes. And the distance that the charring and flame spreads out from the point at which the flame's applied will determine the rating. So the further the flame spreads, the poorer the rating. So this was Class O, which is the best standard, which means that the paint and the aluminium, the thin aluminium facing on this panel, wasn't allowing flame to spread, which is what you want. But nothing of that tested the core. So you get a big fire, nothing like the test, a big fire breaking out of a window affecting this cladding, and it gets to the polyethylene core of this cladding, and then that's flammable, that melts. Now, I don't know if you've got the little video I sent through of no, you haven't, no. But there is a YouTube video which shows a simple test showing polyethylene being set alight, and it drips. It's fire rain, they describe it as. It drips, it melts, it burns very clean. They say it's chemically similar to candle wax. It burns in a relatively clean flame, but it drips and it melts at very low temperatures. So this is the core of the cladding material. Now, what you then have is an ability for the cladding to allow the fire to propagate very rapidly up the building. There are fire stops which are meant to block off the cavity so that any fire getting into the cavity can't propagate up the building. But because this would be propagated in the outer cladding, it would bypass all of that. So all of the fire stops would be ineffective, and the fire would propagate very rapidly up the building. Then what you had was this very large fire was the inner insulation material, the PIR foam, which is quite a durable material. If you had a piece of this and you put a blowtorch on it, it would char and some smoke would come off. And if you take the blowtorch off, the fire would immediately extinguish itself. So it's a relatively, if you test a small piece, it looks very benign. When it's tested in large fires, it produces, at relatively low temperatures, a couple hundred degrees, huge quantities of very toxic black smoke.
Yeah.
And smoke is, of course, the killer. So it was a combination of the outer cladding being changed and the inner insulation providing a source for this black smoke that made the situation so very deadly.
Okay.